Good day everyone. Today, Group 13 consists of Hamza Shafiq, Rulu Adlina, Anik Ifran, Muhammad Izam, Muhammad Naufa, and myself, Yong Hui, will be taking you through our presentation titled The LED Efficiency Gap, Why Green is the Hardest Color. To understand this problem, we first have to look at the challenge shown here on our first slide. While blue and red LEDs have reached incredible levels of performance, green LED are the weak link. Currently, they are significantly less efficient and much dimmer than their counterparts. This isn't just a minor technologicality, it is a massive barrier, because green LEDs consume more power and produce more waste heat. They are holding back the development of perfect, energy-efficient, full-spectrum lighting. Our goal for this project is to explore how we can fix the green LED. By closing this efficiency gap, we can unlock the next generations of advanced lighting system and ultra-efficient display technologies.
Ever wonder how LEDs turn electricity into light? A light-emitting diode, or LED, is a semiconductor device that converts electrical energy directly into light. Unlike traditional bulbs, they are incredibly efficient and rely on a concept called the band gap. The band gap concept: inside a semiconductor, electrons occupy two energy levels, the lower valence band and the higher conduction band. The energy difference between these two is the band gap. This gap is the gatekeeper that controls exactly how much energy the light will have. When we apply electricity, electrons gain energy and jump to the conduction band, leaving holes behind. When an electron falls back and recombines with a hole, it releases that stored energy as a photon, which is the light we see. The size of that gap determines the LED color. As shown in the equation, a large band gap creates high energy blue light, while a smaller gap creates red. By changing the material, we can create any color on the spectrum.
Hello everyone, today we're diving into the green gap mystery. The first point is the cause-lattice mismatch and indium. The problem stems from lattice mismatch. To produce green light, we must increase the indium composition in InGen's LED. However, more indium creates intense compressive strain. This isn't just a physical tension. It shifts the emission but also triggers phase separation and efficiency drop. The second point is the mechanism, QCSE, and defects. This strain induces the quantum confined star effect, QCSE, in a bracket. Essentially, a piezoelectric field pulls electrons and holes apart within the quantum well, making it harder for them to recombine and emit light. Simultaneously, a strain creates defects, non-radiative recombination centers where energy is lost as heat rather than light. In the conclusion, ultimately, to solve the mystery and produce efficient green LEDs, we must find ways to reduce these internal electric fields and minimize defect density. Thank you.
Let's examine the efficiency and quantum loss analysis. The core metric here is internal quantum efficiency. It measures how effectively injected charge carries produced proton. Mathematically, it's the ratio of radiative current to the total current. Efficiency is a competition. While we aim for radiative combination to emit light, we often face non-radiative recombination where energy is lost as heat. This happens through three main mechanisms: SRH via material defects, UGA recombination at high carrier densities, and surface recombination at the sidewalls. This loss is most evident in the green gap. The drop in efficiency between 520 and 560 nanometers. This occurs because green light requires high indium content, leading to lattice mismatch and strong stark effect. These internal heats physically separate electron and holes, drastically lowering the radiative rate while increasing UGA loss at operating currents. In short, managing these internal quantum losses is the key to losing the green gap and achieve high brightness green LEDs.
Industry standard for bypassing the green gap. Instead of struggling with unstable high indium crystal, we utilize a high-performance blue LED engine. By applying a coat of advanced narrowband phosphorus, we initiate a process called down conversion. This converts high-energy blue photon into consistent vibrant green light. The physics here is governed by the stroke shift following the equation E equals to h(c) over lambda. We know blue light has more energy than green, while this energy difference is released as heat. Our use of LUAG phosphorus minimizes this heat tax, ensuring 90% quantum efficiency even at high temperature. This hybrid pivot provides a reliability and color purity needed for next generation display and national energy infrastructure. It is a scalable, cost-effective solution that is ready for implementation today. Industry standard for bypassing the green gap.
Hi everyone, my name is Nura Adina binti Zaldi, and today I will briefly explain about thermal management and its impact on LED. High brightness LED operate at high current, so not all electrical energy is converted into light. A significant portion is released as heat at the LED junction. This will cause the LED to get hot. So the main sources of heat are electrical resistance loss, non-radiative recombination, and also post-purge conversion loss in a white LED. If this heat is not controlled, this will lead to the reduce light efficiency, color duration, and even make LED lifetime become shorter. Thermal management is very important. Components like heatsink and thermal material will help transfer heat away from the LED junction and maintain a safe operating temperature. Heat will flow from the LED junction to the heatsink, and then it will go to the surrounding air. With proper thermal management, LED will become more energy efficient, consume less electricity, and help reduce carbon emission. And also, maintenance costs will become lower. Thank you.